Namaste. Last time we were discussing this molecular orbital theory, and in which we have seen the first or preliminary parts of this topic, that is the s orbitals, p orbitals, d orbitals, atomic orbitals, and their linear combinations to form the concerned molecular orbitals. Now we have to see this molecular orbital mixing. Here we will see what approaches are there to explain this orbital mixing, and what are the influences or consequences of this orbital mixing. So we will discuss these things one by one. So up to this time we have seen the atomic orbitals which are having similar energy and identical symmetry can undergo interactions with each other. So this condition of interaction between the atomic orbitals is possible only when the symmetry and energies are nearly identical. The energy may be slightly different, but symmetry should be accurate. Then only there is possibility of interaction between such atomic orbitals. So there are two approaches. So we have two approaches to explain this orbital mixing. So the first approach shows that the molecular orbitals of same symmetry and equal energy, nearly equal energy, shows orbital mixing, So because of such interactions, or we can say shows mixing, means what is mixing? Mixing means interact with each other, that is called mixing. And second approach is that the atomic orbitals of same symmetry and nearly equal energy undergo interactions with each other, or they interact with each other. So because of such interactions, so we will see the first type. We will see this first type of interaction between the molecular orbitals of same symmetry and nearly equal energy. So when the molecular orbitals of same symmetry and nearly equal energy, when interact with each other, the result is that the molecular orbitals of lower energy will show still lowering of their energy levels, and molecular orbitals of higher energy will go up in energy. So this is the effect of the orbital mixing. Now in order to understand this, we will consider the molecular orbital diagrams. Last time we have seen the general molecular orbital diagram, and we will see also the molecular orbital diagram which results after mixing of or interaction of molecular orbitals of same symmetry and nearly equal energy. So we will remove this in order to have more space. So this is our energy axis, and we are showing the atomic orbitals. So we will show here the atomic orbitals only that are required for orbital mixing. So 1s orbital is not required, so we will not take this orbital here, but it is actually there, so that is not required. So we consider this 2s orbital. So this is 2s and another 2s. So this is for atom A, and this is for atom B, for same, that is homo-nuclear diatomic molecules. So as a result of this, that will undergo a linear combination to produce the bonding molecular orbitals and anti-bonding molecular orbitals. So this is sigma G 2s. This is sigma star U, that is 2s. Then we will have another orbital, that is 2p. So there are 3 such energy orbitals in this. So this is 2p. So this is first atom, second atom, that is A and B. So after linear combination, they will produce this bonding molecular orbital called sigma G 2p. So this is sigma G 2p. Now we will have the molecular orbitals of pi nature. So we will show this. These are the two. There are 2 such orbitals which are called Biosymmetry Orbitals. There are 2 Biosymmetry orbitals. There is only one sigma G symmetry orbital. Then there is there are such, these are pi G symmetry, pi G star symmetry molecular orbitals, and this is sigma U star symmetry orbital, that is 2p. Is obtained from 2p orbitals. So these are the 2 important. Now here you will find that here 2s has sigma symmetry. So both these, there are 2 such 2s orbitals having sigma symmetry. There are here 2 pz orbitals, 1 pz here, 1 pz here. So they are also having sigma type of symmetry. Their energy difference between 2s and 2p is not much more. There is less. Means this sigma G molecular orbital, this and this sigma G this sigma orbitals resulting from 2p. So these and these are also having very close to each other. So they can undergo interactions. So they will interact with each other, and as a result we will obtain the new diagram. So that is having structure like this. Say this is 2s. This is also here 2s of A, 2s of B. But here you will find that there is no mixing, and there is mixing of MOTs, molecular orbitals. So after this, as a result of mixing, what happens? the or molecular orbitals after undergoing interaction with each other shows lowering of energy of the lower molecular orbitals. So these sigma g are lower energy, so they will show fall of energy. So their energy will decrease like this. So you will find that there is decrease in energy. So this is sigma g of 2s. So compared to this sigma g to s, it will go down, and compared to this sigma u star, it will also go down. So this is sigma star u of 2s. So compared to this sigma u star, it is still lower in energy. Now I will go to this 2p orbitals. So these 2p and 2p are also of same energy. So we will show here close to this and these 2p. So after orbital mixing, so this sigma g will undergo mixing with each other. As a result of this, the energy of this sigma g2p will go up. This will also go up. So as a result of this sigma g will go above this pi u. So we will find this here pi molecular orbitals of the same energy, that is pi u orbitals of bonding nature. Then you will find that as a result of this, the sigma g is moving in energy above pi u. So we will show here this sigma g of 2p. Then the pi antibonding molecular orbitals will remain at this same energy level. So this will remain at same energy. So we will show that this is pi g star, and this sigma u will still go up in energy. So this is sigma u star 2p. So this will be the effect because of orbital mixing between the sigma molecular orbitals. So there are 4 sigma orbitals, 1, 2, 3 and 4. Similarly here 1, 2, 3 and 4. So these sigma orbitals we will show in one color. So this is sigma g orbital, that is of 2p nature, 2p resulting from 2p. So these diagrams will tell you that after orbital, before this is without mixing and this is with mixing. So without mixing the energy levels are like this, but after mixing sigma u, which is here lower energy, it will go above the pi u molecular orbitals, and these energy levels are compared to this will go down. So this is the one approach, that is interaction between molecular orbitals. Now there is second approach indicating atomic orbitals of same symmetry and nearly same energy G will interact So we know that there are two s atomic orbitals. 2s atomic orbitals of this, or one is A atom and B atom. So atom A will have one 2s, atom B will have another 2s. Now there are two pz orbitals of atomic orbitals. So these are from 2pz of A and 2pz of B. So we can also write here this to make it clear. 2s of A plus and 2s of B. So in this way there are four such atomic orbitals having same symmetry and nearly same energy. So they will undergo interaction and they will produce four molecular orbitals. They will produce four molecular orbitals. And what are these molecular orbitals? So these molecular orbitals are indicated by this equation, that is psi. So psi indicates the resulting molecular orbital. So this is given by psi is equal to C1 into psi 2s A plus or minus psi 2s plus or minus C1 C2 into psi 2s of B plus or minus C3 into psi 2pz of A plus or minus C4 into psi 2pz of B. So this is the equation which will explain the mixing of the four atomic orbitals which are indicated by 2sa, 2sb, 2pza and 2pz of B. So such four atomic orbitals will interact with each other and they will produce four molecular orbitals. But here you will find that this mixing means you will find that the atomic orbital of 2s nature, this 2s nature and this 2p nature, when come together and they will produce the molecular orbitals of equal nature. So what will be the result? Each molecular orbital will have some s characters and some p characters. So every four means each of these four molecular orbitals resulting from this combination will have both types of characters, s plus p characters. So depending upon the extent or magnitude of s and p characters, the shapes of these molecular orbitals will be different than the shapes which are expected from the molecular orbitals without mixing. So for example, you can have say there is a combination like this. So it will have some s characters and p characters. So the bond and molecule will also show there some s characters and p characters. So this will also result. So these four molecular orbitals that are produced will show again the same result which we have shown in the diagram for orbital mixing. What are the results? The two of these, there are four molecular orbitals, out of which two will show lower energy level than without mixing. And the remaining two orbitals, molecular orbitals, will show increase in their energy levels. Means they will go up and two will go down in energy axis. So as a result of this, the properties, magnetic characters are also easily explained because of such mixing. Now it is important to note that this type of orbital mixing is observed for elements or molecules having elements from lithium to nitrogen. So this type of orbital mixing is observed for elements or their compounds like the molecules, the homo-nuclear diatomic molecules from lithium to nitrogen. But afterwards, this type of combination means orbital mixing is not shown. Specifically, the molecules like B2 and C2 are showing this orbital mixing with great efficiency. So that is separate part. So that will be discussed whenever we come across a molecular orbital diagram for these two molecules. And so here we will find that in molecular orbital diagram, the bonding molecular orbitals are lower in energy, antibonding molecules are higher in energy, but there may be some other molecular orbitals lying in between them. So they will come closer to the non-bonding level, means the energy level of the original atomic orbitals. Means they are not exactly coming in that direction, but they will come closer to that. So because of such, the intermediate molecular orbitals will show some bonding characters and some antibonding characters, and because of this they are behave like non-bonding molecular orbitals also. So this is the impact on the properties of molecules here you will observe. So with this we will stop our discussion and we will continue in the next lecture. So see you next time. Please subscribe to this channel, share the channel, and also press like button and bell icon button. So thank you very much for watching this.